To type hint or to not type hint? That has been an extremely hot question in Python for about the past decade. We often encounter blanket statements that type hinted or statically typed code is just better. But why might it be better? And importantly, why might it be worse? But first, PEP-484 type hints have been around for about a decade now. And the annotation syntax that we've been seeing in Python has been around even longer than that. These features have been used in an incredible number of ways and have enabled static code tools and analysis tools and many more features than that. There's so many different applications that we'll cover about the annotation syntax. But today, overall, we're going to take a dive into the world of annotations and type hints to finally address the question, should I actually be using type hints in my code? I've seen arguments from every which side of things. Proper type hinting becomes more cumbersome than helpful, which in my experience is more so the problem with the problem. But type hinting has also led to a number of different very useful tools that we can use in Python, such as MyPy, as well as establishing some structured syntax for creating and using types in Python. So let's go ahead and we're going to dive into this, and we'll start off with a discussion of function annotations. Function annotations were introduced in PEP-3107, but what were they all about then? Well, it laid the groundwork for what is Python's modern type hinting system. They effectively said, we know that we want to implement some of these static types or annotations onto function arguments, but we don't know what shape or form they're going to take. So right now we're just expanding Python syntax to simply allow annotations on function arguments. And so what this means is I can write a Python function and I can annotate its actual arguments. So here in this case, I have an unannotated function, and you can very well see that, well, just glancing at it, x's is probably supposed to be a list. IDX0 and IDX1, those are probably going to be integers because I'm swapping the values or swapping the locations of two values within x's. And that's the whole point of this function. I take some input, 1, 20, and 300, and then I swap the first two positions and I result with 21 and 300. Now, there are no type hints or no annotations, I should say, on this function, but yet us as readers of this program can look at this function and decide for ourselves what it might work on and what it might not work on. And so just by reading the code, we know that x's has to be indexable. It has to support at least get item, and that IDX0 and IDX1 are likely to be integers. Now, one case in point here is that x's could be, say, a dictionary, and IDX0 and 1 could be strings, or they could be really any hashable type. And so we can't make all the assumptions, but we can make reasonable guesses. This is one of the strengths of Python, is that these generic functions that operate on generic types, meaning this could be a list, it could be a dictionary, it could be anything that supports that get item syntax. Well, we can work on this, and we don't actually have to specifically declare that, well, this version of the function only works on a list. This version of the function only works on a dictionary. And so we can use the same syntax to interact with multiple different Python objects. But let's say we actually really want to limit this down to just one type. We want to say that x's has to be anything that's ordered and implements get item. This is what Python refers to as a sequence, and this syntax was, of course, introduced in our PEP-484 type hints. But what I might do is just naively write in a comment. I'm describing my types. I'm not using the function annotation syntax, but I am describing the types of my objects. And when I run this function, if we inspect the help, here's the issue, is the only way this comment is somewhat useful is if I actually look at the source code. And if I'm already looking at the source code, I can probably infer what the comment was trying to explain without actually having the comment there. And so maybe a comment isn't the most useful place to put this type hint information. Maybe I should be using a docstring. And so now with the docstring approach, I can say that x's is some sequence, IDX 0 and 1 are indices, so integers in this case, and I can actually call help on this function. You see I get a nice helpful output, or a nice documentation, a string here that tells me what this function's actually expecting to deal with, at least when I wrote it. But there's an issue with this. There's no structuring to this documentation. I would have no way of going in here and programmatically accessing any of these values in order to actually work with them, whether I'm developing a static code analysis tool or I want to have some fun with dynamic runtime at Python using these pieces of information. Well, we can add some structuring around our docstring. We can take something like NumPy docs format, and we can properly document our variables or our arguments here to our function. We can specify their types that we're expecting them to be, and we can add a little helpful text describing what this function does with each of these values. We can even specify a return, whether or not this function returns something. You can see here that we implicitly return none since we have a mutable operation that we're relying on. And the nice thing here is that when I ask for the help, I get a very nicely structured documentation, one for one, exactly what I wrote prior. But here's the issue. This is useful for reading, and that is it. I can not do anything programmatic with this docstring. We can parse these values out to try and make sense of them in order to work with them, but there's always going to be an ambiguity of what is sequence and where did it come from? Well, I would have to actually run this code, evaluate all of this code, and try to infer where sequence points to in Python's namespace. And there's no guarantee, since this is just a string, if I have a typo in this sequence, there's no way any tool that I write, dynamic or static, will ever be able to infer what this type is supposed to be. And so what we can do is we can try our best to parse out that information in order to make some use of it. And I'm going to have to do just a couple of tricks here in order to parse that docstring line by line. And I'll use nwise in order to preserve some state. I need to know, am I creating parameters or am I creating a return value? And I'm going to try and capture this information. I'm going to try to capture that x's is a sequence, IDX 0 is an integer, IDX 1 is also an integer, and then the return value is just none, which is of course, right, a none type. And so if I parse this apart just right, we can actually access some of that useful information. I can look at the parameters of this function, and I can programmatically see that, oh, x is a sequence, IDX 0 is an int, and so on and so forth. The issue here, though, is that these are all represented or intermediated by strings. I don't have access to the actual classes, the actual sequence type, or the sequence class in this case, that's backing, right, this x's value. And so while I can parse a structured documentation, oftentimes it's not the most useful thing to programmatically access. This is primarily for human consumption, human reading, or documentation, automatic documentation purposes. Now, when we look at annotation syntax, we're going to see a very close semblance with what we just saw with the NumPy doc. Specifically, we specify an argument, and then we use a colon to specify the expected type of that argument. Now, by itself, this does absolutely nothing. Python will not automatically check to see if x's is actually a sequence at runtime. IDX 0 will not be checked to see if it's an int at runtime, and we're not going to check if swap actually returns none at runtime. This is purely for human consumption at this point in time. However, what this does mean is when I look at the help for this function, I can actually see very clearly what all of these arguments are expecting, or what the types of these arguments are expecting. And so if I ever run this code and I end up getting a type error back out, well, this might help me mediate or remediate that type error that I see. Additionally, PEP-484, which was the function annotation PEP, added in a dictionary that we can access in order to understand what these type hints are and how we can work with them. And so just by looking at the __ annotations attribute on a given function, we can have programmatic access to these values. And from here, you can do some very neat things. So let's talk a little bit about what else PEP-484 can be used for. One of the earliest ideas after this PEP came out, this was popular for a number of years after this PEP came out. People tried every which way to see what they could do with the annotation syntax that wasn't necessarily just annotating. We can insert extra pieces of logic actually into these annotations, and then we can use decorators in order to patch into those type hints, or patch into those annotations, I should say, and do some very cool things with them. And so what I can do here is I can define a function that takes two inputs, x and y. By adding in our smart defaults decorator, we can actually check to see what type hints are just annotations, and then we can do very fun things with those type hints. Specifically, what this is going to do is it's going to say that by default, the default argument for y is always going to be 2 times that of x. And so when I run this code and I actually evaluate the values of x and y inside the function scope, you can see that the default argument for y, which I'm not changing manually, changes depending on the value of x, and our default argument for y is always going to be twice of x. And so we can use annotations to inject behavior, or to declare behavior, I should say, that's going to be dynamically created at runtime, or dynamically determined. What else we can do with these type hints is that we can perform dynamic type checking. And now this is going to be a little bit different than static type checking, which is what we'll talk about later, but let's dive into what dynamic type checking is. Well, Python allows us to, as we just saw, to kind of hijack some of the annotation syntax and perform dynamic runtime evaluation operations on that while our program is running. And what this means is I can appropriately declare the types that this function accepts, and then I can wrap it in a decorator, and all this decorator does is check the types. Is this type a subtype or an instance, right, of the type declared? And so what I can do here is I can define my function, and I can run this, and I can say, okay, swap my x's, which is a list, and pass in IDX 0 and 1. So swap positions 0 and 1. This works, and we wouldn't expect it not to. Going on to a test case, well, I can pass in a string for one of my index positions, and of course that's not going to work. But what we see here is that before the function was actually called, we intercepted that call, and we said that, oh, this is an error, right? IDX 0 is expected to be an int, but we encountered a string. And I can have a fairly detailed, right, check as to what Python's actually expecting and why this didn't work. And of course, this will work with any arguments of any types, right? As long as it's not an integer and a sequence in this case, then we're going to fail our check. Now, I can of course turn off this checking. You can see here we're using our debug flag. So if I just pass Python capital O, -O here, we end up, right, circumventing that step check, and we end up on a similar but slightly different error. Now, we'll get into the nuances of what this error is telling me versus the previous error. This error is telling me that the function that I called within the function, the getItem syntax, is expecting an integer, not a string, but there will be a small, minute difference that we'll discuss versus catching an error early versus catching an error right while the function is executing. And so let's move on to talking about what else we can do with these annotation syntax. We can supply preconditions and postconditions. In this example, I'll focus just on the preconditions though, but we can take our decorator, our check decorator that we just wrote, and we can make it a little bit stronger. I can make it a little bit more dynamic. Specifically, I can actually examine the call signature of my swap function, and I can dynamically inject arguments into predicates. Now, we can see here preconditions is just a list of lambda functions or a list of anonymous functions. What my decorator is doing is it's analyzing the arguments expected from this lambda, and then it's passing in the arguments from my swap function. So every time I call swap, I'm going to pass x's into this precondition, and if this evaluates to false, well, I know we failed to check some type of precondition, and I should return an error. And so what this would look like if I swap my x's, right, with all valid arguments here, well, we end up receiving no errors. But now, in this case, I'm going to try to swap position 0 and 10 instead of just 0 and 1. Swapping positions 0 and 10 will err out on me for the reason that it failed our precondition check number 1, which is asserting that each index has to be less than or equal to the length of the sequence that it's operating on. And so here you can see that I'm passing in, right, the length of our x's here, and I should probably pass this in as well. But you can see that Python's dynamic or runtime capabilities are immense. We can do almost anything that we want at the Python runtime with a little bit of decorators and just using this function annotation syntax. And for a long time, that is what Python's function annotations were used for. They have been used in this fashion to perform runtime-based checks, perform any type of balance checking as well, or even in your favorite APIs, right? Things like Fast API, things like Typer or Magic GUI, they all use type hints in order to inform their programs. And in the case of something like Fast API or Pydantic, right, it will use those types possibly to even try to convert values passed into those types as a part of sanitization.